The story of the universe often begins with light, yet the mystery that reshaped modern cosmology began with something far more subtle. It began with motion. When astronomers first pointed their telescopes toward distant galaxies, they expected the great spiraling systems to obey the familiar pull that had shaped the motions of planets around our own quiet sun. For centuries, Newtonian gravity had described those motions with astonishing accuracy. Every falling apple, every circling moon, every sweeping orbit could be understood through the simple idea that mass pulls on mass. Later, Einstein would show that gravity is not truly a force, but a bending of space and time itself, a curvature that guides planets and stars along paths carved by mass and energy. Yet even with this deeper insight, astronomers believed the motions of galaxies should still follow the same central rule. If you know how much matter something contains, you can predict how fast it should move. That belief held until observers began to measure the true speeds of stars in the outer regions of spiral galaxies. The expectation was straightforward. Stars near the center should move quickly, pulled by the dense concentration of mass, while stars near the edge should slow down, just as planets far from the sun move more gently around it. Instead, those stars did something profoundly unexpected. They did not slow down. They moved just as fast as the ones near the galactic core, sometimes even faster, as if gripped by a gravitational pull far beyond what the visible matter could provide. These motions made no mathematical sense within the known inventory of stars, gas, and dust. Something was missing, something exerting gravitational influence without releasing a single trace of light. Long before the full weight of the problem settled over astronomy, Fritz Zwicky had already seen a hint of it. In the 1930s, he studied a collection of galaxies known as the Coma Cluster, a vast congregation of thousands of galaxies drifting through space together. Using their motions, he calculated the mass required to keep the cluster gravitationally bound. The galaxies were moving too quickly to be held together by the matter astronomers could see. If Newtonian gravity was correct, the cluster should have flown apart long ago. Zwicky proposed that a large quantity of unseen matter must exist, far more than what telescopes revealed. At the time, the idea was considered bold, almost extreme, yet the math was unambiguous. Still, the evidence was thin, and astronomy did not yet recognize the magnitude of the puzzle he had uncovered. It would take decades before the mystery returned with overwhelming clarity. In the 1970s, Vera Rubin and Kent Ford set out to measure the rotation curves of spiral galaxies with unprecedented precision. They expected to see the graceful decline in speed predicted by standard gravitational models. Instead, the data from galaxy after galaxy showed the same perplexing pattern: rotation curves flattened, refusing to drop. The stars were orbiting too quickly, and the galaxies were not flying apart. Something invisible was holding them together. Rubin's measurements were careful, repeated, and verified across countless systems. The conclusion was unavoidable. The universe contained far more mass than anyone had previously imagined, and most of it was invisible. NASA joined the investigation through missions that mapped stars, gas, and interstellar structure with instruments far more sensitive than those available in earlier eras. With space-based observatories free from atmospheric distortion, astronomers could measure how galaxies moved, how clusters behaved, and how massive structures bent the fabric of space and time. The results pointed consistently to the same unsettling truth. The visible universe was only a small fraction of the actual mass-shaping cosmic motion. Yet this was not merely a discovery of missing brightness. It was a discovery of missing physics. Gravity, whether described by Newton or Einstein, demands that motion matches mass. When the motion is far stronger than the visible mass can produce, something fundamental is wrong. Either gravity behaves differently on large scales, or there exists a vast quantity of matter that does not interact with light. In the early stages of this realization, astronomers leaned toward the second explanation. It required fewer disruptions to establish theory, and it aligned with the growing body of observational evidence. Still, the identity of this unseen mass remained out of reach, hidden behind the veil of space itself. The more precisely astronomers measured galactic rotation, the more undeniable the discrepancy became. Large elliptical galaxies, small dwarf galaxies, sprawling spirals, and dense clusters all exhibited the same gravitational signature. The pattern repeated across the cosmos, from our own galactic neighborhood to the farthest systems reachable by modern instruments. It was not an isolated oddity. It was a universal feature. The universe was filled with mass that emitted no light and absorbed none. This was the gravitational problem that no one had expected, but everyone now had to confront. Einstein's general relativity offered the language to describe these motions, but it could not conjure mass where none existed. The equations responded faithfully to whatever mass and energy were present, but they assumed astronomers could identify those components. When the cosmos behaved as though it were heavier than it appeared, the equations simply reflected that greater weight. The missing ingredient had to be physical, not mathematical. As NASA extended its reach through deeper surveys and broader mapping programs, the picture grew sharper. Galaxy clusters bent the path of background light more strongly than visible mass allowed. Gas clouds in clusters moved faster and reached higher temperatures than expected. The gravitational signals were unmistakable. Something enormous, powerful, and invisible was shaping the universe on every scale. And yet, despite the magnitude of this discovery, the identity of the missing mass remained silent. It did not glow, did not scatter photons, did not collide like ordinary matter. It revealed itself only through its gravitational pull. This invisible presence seemed to wrap around galaxies, pool within clusters, and thread through the cosmos in a pattern that suggested structure far beyond human sight. As astronomers faced the puzzle, the path ahead became clear. If galaxies should fly apart but do not, then something unseen must be holding them together. And to understand that unseen influence, we must learn how to measure what cannot be seen at all. The universe has always spoken in the language of motion, but it is a quiet language, one that reveals its secrets only to those who watch patiently. As telescopes improved and spectral instruments became more refined, astronomers learned to measure the smallest shifts in starlight, changes so subtle that a human eye would never detect them. These shifts, encoded in the wavelengths of light, told observers how fast stars were moving around their galactic centers. The technology behind these measurements grew steadily more precise, allowing scientists to chart the rotational behavior of galaxies with a clarity that previous generations could not have imagined. It was in these details that the gravitational mystery deepened. The stars orbiting the outskirts of galaxies behaved as though they were responding to a gravitational presence far larger and more extended than the luminous matter suggested. If only stars, gas, and dust were present, outer stars should drift more slowly. But instead, their speeds remained high and steady, as though enveloped in a vast halo of unseen mass. This pattern was not a rare oddity, but a universal rule. From faint dwarf galaxies to enormous spirals, rotational velocities refused to fall. Each observation reinforced the same conclusion. Something unseen was shaping the motion of matter throughout the cosmos. This was where the conversation between observation and theory became delicate. Newtonian physics, though powerful, was not designed to describe the dynamics of entire galaxies. Einstein's general relativity offered a more complete picture, yet it too required knowledge of the mass distribution within a system. Without knowing where the mass is, the curvature of space cannot be fully mapped. Astronomers soon realized that the mismatch between predicted and observed motions was too large to be explained by hidden gas clouds or faint stars alone. The gravitational influence was far beyond what any known form of matter could supply. If the galaxies were to hold together, a massive but invisible component had to be present. The idea of unseen matter forced a shift in the scientific mindset. Until then, the cosmos was thought to be mostly transparent. Light revealed the universe, and what could be seen was assumed to represent what existed. Now astronomers faced the possibility that their brightest instruments were only detecting the smallest fraction of what truly made up the universe. If most of the mass did not emit or reflect light, then telescopes were merely brushing the surface of a deeper cosmic structure. NASA's growing fleet of space-based observatories provided an opportunity to test this possibility in new ways. Freed from atmospheric distortions, instruments aboard satellites could collect light across a broad range of wavelengths, from ultraviolet to infrared, revealing structures otherwise hidden from ground-based observatories. As these missions expanded the map of the universe, they consistently showed the same gravitational pattern. Galaxies bent light more strongly than their luminous material allowed. Their motions suggested a deeper well of gravity extending far beyond their glowing disks. It was becoming increasingly difficult to ignore the invisible. Yet even as the evidence grew, the nature of this unseen mass remained elusive. Scientists could estimate how much of it must exist, where it was concentrated, and how it influenced structure, but they could not detect it directly. Traditional methods of observing matter rely on interactions with light, but this mysterious component did not seem to interact with light at all. That silence made it far more challenging to study. The growing body of data followed a similar arc in clusters of galaxies. These immense collections of stars, held together across millions of light years, provided another arena in which gravitational behavior could be tested. Astronomers calculated the velocities of galaxies within clusters and found that the systems should disperse rapidly if only visible matter were present. The kinetic energy of the galaxies exceeded the binding energy provided by the luminous mass. To remain intact, clusters needed far more gravitational glue than telescopes could identify. This was precisely the discrepancy that Zwicky had uncovered decades earlier, and now it was being confirmed with higher precision and far better observational tools. Measurements of hot gas in clusters strengthened the puzzle even further. X-ray emissions revealed that the gas reached temperatures so high that it should escape the cluster's gravitational grasp unless an enormous amount of mass held it in place. Once again, the visible matter failed to account for the necessary force. These repeated observations formed a consistent narrative. There was more to the universe than met the eye. With each piece of evidence, astronomers faced a narrowing set of possibilities. Either the universe contained vast quantities of an unknown form of matter, or the laws governing gravity behaved differently on cosmic scales. Both ideas demanded courage, but one was becoming far more consistent with the growing data. The simplest explanation was that the mass was real, physical, and present, but invisible. This approach preserved the framework of general relativity while acknowledging that the inventory of matter in the universe was incomplete. As NASA prepared deeper surveys and more refined observations, the picture became increasingly clear. The motions of galaxies, the temperatures of cluster gas, and the bending of light all pointed toward the same conclusion. Something unseen permeates the universe, outweighing the luminous material by a substantial margin, and yet, this invisible mass is perfectly consistent in how it influences gravity. It behaves as though it is there, even though it eludes direct detection. The gravitational problem was no longer an anomaly. It was a cosmic truth waiting to be fully understood. The universe was heavier than it appeared, and that extra weight was shaping the evolution of galaxies, clusters, and the large-scale structure of space itself. But how could astronomers measure something that refused to emit light? How could they study a presence that revealed itself only through the curvature it created? These questions paved the way for a new kind of astronomy, one that explored shadows not by sight, but by the distortions they left behind. If we cannot see the missing mass directly, perhaps we can still trace its influence. And that search begins by learning how to measure what cannot be seen at all. The universe often hides its most important truths behind the quietest clues, and gravity has always been the most patient messenger. Even before astronomers understood what they were looking for, The cosmos had already drawn the outlines of the invisible. Every rotation curve, every cluster measurement, every subtle shift in starlight was part of a larger pattern waiting to be recognized. As new instruments reached into deeper regions of space, that pattern sharpened. The question was no longer whether something unseen existed. The question became how such a vast and silent presence could shape the universe so completely while remaining entirely hidden from the senses. When astronomers first mapped the distribution of visible matter in a galaxy, they noticed that most of the starlight was concentrated in the central bulge and the surrounding disk. The luminous material tapered off near the edges, fading into faint streams of gas and dust. If the mass distribution followed this light, as it does in planetary systems, then the gravitational pull should weaken with distance. But the observed motions did not follow the shape of the glow. Instead, they pointed to a gravitational field that remained strong far beyond the regions where stars grew thin. This meant that the true mass of a galaxy was distributed differently from the light it emitted. The stars were tracing the edges of something much larger, something whose boundaries extended far past the bright spiral arms. In time, astronomers would call these vast structures dark matter halos, immense reservoirs of invisible mass within which galaxies formed and evolved. The realization that galaxies were immersed in halos of unseen matter changed more than the way astronomers interpreted motion. It changed the way they saw structure itself. The universe could no longer be understood purely through the light it produced. Nearly all visible matter was embedded within an envelope of something else, something that shaped gravitational landscapes on scales far beyond human experience. And yet, this unseen component remained perfectly smooth and calm, interacting only through gravity, leaving no trace of collisions or heating that would betray its presence in more familiar ways. As NASA expanded its observational capabilities, evidence accumulated from every region of the electromagnetic spectrum. Radio telescopes mapped the cold gas within galaxies. Infrared instruments revealed star-forming regions hidden behind dust. X-ray observatories charted the hot, diffuse plasma in galaxy clusters. Optical telescopes traced starlight across billions of years of cosmic history. No matter which wavelength was used, the conclusions aligned. The luminous universe accounted for only a small fraction of the gravitational behavior astronomers observed. The overwhelming majority of mass remained dark. In clusters of galaxies, the gravitational problem appeared on an even grander scale. If a single galaxy could hide large quantities of unseen mass, then an entire cluster could amplify the discrepancy to enormous proportions. Measurements showed that the galaxies inside a cluster moved with astonishing speed, as though swimming in a deep gravitational well far more massive than their combined starlight could explain. X-ray studies of the hot gas provided a second line of evidence, revealing temperatures so high that the gas should escape unless restrained by a tremendous gravitational force. The cluster was acting as though it contained several times more mass than the visible matter provided. This consistency across multiple independent observations left little room for alternative explanations. Gravitational lensing offered yet another window into the unseen. According to Einstein's general relativity, mass bends the path of light. The more mass present, the stronger the bending becomes. Astronomers realized they could use this effect to map the mass distribution of galaxy clusters without relying on visible light at all. When NASA and other observatories collected images of distant galaxies whose light passed near massive clusters, their shapes appeared distorted, stretched, or magnified. These distortions provided a direct measure of the gravitational field. When the mass maps derived from lensing were compared with maps of visible matter, they rarely aligned. The gravitational lensing revealed immense concentrations of mass where little or no luminous matter existed. This was one of the clearest demonstrations that the universe contained far more than what human eyes could detect. Each of these lines of evidence carried its own uncertainties, yet together they formed a cohesive and compelling narrative. The missing mass was not a trivial amount. It dominated the structure of galaxies and clusters. Even more strikingly, its influence was essential for the formation of the universe as we know it. Without the additional gravitational pull provided by this invisible matter, galaxies would not have formed so early in cosmic history. Stars would not have gathered into stable systems. The delicate tapestry of the cosmic web could not have emerged in its familiar pattern. Still, as powerful as this conclusion was, it carried a profound discomfort. Astronomers had built their understanding of the universe on the assumption that what could be seen represented what existed. Now, the evidence suggested the opposite. Most of the universe was invisible, and the visible parts were merely scattered traces within a much larger structure. The cosmos was not a glowing expanse, but a dark framework with islands of light floating within it. The gravitational problem forced astronomy into a new era, one in which traditional observation was no longer enough. The challenge now was to measure the invisible, to infer the unseen, to understand mass not by its brightness, but by the way it shaped motion and bent the fabric of space. The mystery of dark matter was no longer just a question of missing mass. It was a question of the true nature of reality, hidden behind a veil of gravity. As the chapter of discovery closed and the chapter of deeper investigation began, astronomers faced an extraordinary task. To uncover the identity of the unseen mass, they would need to develop new tools, new methods, and new ways of reading the universe. They would need to learn how to measure what cannot be seen directly. And that journey begins with the next step into the invisible, where gravity becomes the guide for everything the eye cannot reveal. The universe does not always reveal its contents through the glow of stars or the shimmer of distant galaxies. Much of what exists leaves no trace of light, and yet it shapes the cosmos with undeniable strength. To study something that does not shine, astronomers must rely on the one messenger that never lies: gravity. It is the only signal that dark matter sends, and so the tools used to study it must be designed to read distortions, motions, and subtle patterns in space itself. Measuring the unseen is not a matter of looking for illumination. It is a matter of reading the faint imprints left behind by invisible mass as it bends and sculpts the universe. The journey begins with Einstein's realization that gravity is not a force, but a curvature. When mass is present, space and time warp around it, creating a landscape of valleys and ridges along which light and matter must travel. If an unseen mass lies between the observer and a more distant galaxy, the background light will curve as it passes through the distorted region. This bending changes the shape of the distant galaxy's image. It may appear stretched or magnified or shifted slightly from its true position. These distortions provide a direct measure of the gravitational field, revealing the presence of mass even when that mass emits no light at all. This phenomenon, known as gravitational lensing, has become one of the most powerful tools for studying dark matter. Strong lensing occurs when the curvature of space is so intense that it creates multiple images of a single background galaxy, or forms elegant arcs of distorted light wrapped around a massive cluster. These arcs are not artistic flourishes of the universe. They are measurements, precise and calculable, providing astronomers with a map of how mass is distributed across the cluster. The luminous galaxies and the hot gas seen in X-ray wavelengths account for only a fraction of the gravitational pull inferred from these arcs. The rest must come from something dark. But while strong lensing reveals dramatic features, the majority of the cosmos is shaped by gentler distortions known as weak lensing. In this regime, the bending of light is subtle. Background galaxies appear slightly stretched or aligned in preferred directions, patterns that would be invisible without studying thousands of galaxies at once. NASA's Hubble Space Telescope has produced some of the most detailed weak lensing maps ever created, tracing the hidden scaffolding of matter that threads the universe like an intricate web. The upcoming Roman Space Telescope is expected to refine these maps even further, scanning enormous regions of the sky with extraordinary precision, revealing the distribution of dark matter with clarity that earlier generations could not imagine. These lensing methods provide a direct gravitational measurement, But they are not the only way astronomers study the invisible. Another powerful tool lies in the faint afterglow of the early universe, the cosmic microwave background. This ancient light, stretched over billions of years, carries imprints of density fluctuations present when the universe was young. Tiny variations in temperature, measured with exquisite accuracy, reveal how the early universe responded to gravity. These variations show that ordinary matter alone cannot explain the pattern. The cosmos required an additional gravitational component, one that interacted only weakly with light, yet dominated the formation of structure across vast scales. Without dark matter, the early fluctuations would have evolved into a universe far smoother and more diffuse than the richly structured cosmos we observe today. Clusters of galaxies offer yet another window into the invisible. By measuring the temperature and motion of the hot gas that fills these clusters, astronomers can determine how strongly gravity must act to keep the system bound. The gas remains trapped only because the gravitational pull is enormous, far greater than what the visible galaxies can provide. X-ray observations from Chandra and other space-based instruments show temperatures so extreme that in the absence of dark matter, the gas would have evaporated into intergalactic space long ago. Orbital dynamics extend the toolkit even further. When astronomers track the motions of galaxies within a cluster or study the paths of stars orbiting within a galaxy, they can calculate the gravitational pull required to keep those objects on their observed trajectories. Again and again, the measurements show the same truth. The speeds are too high. The systems should not remain intact unless a vast quantity of invisible mass surrounds and permeates them. Across all of these methods, the conclusion is consistent. Dark matter reveals itself not through light, but through the distortions and motions it creates. Gravity becomes a tracing instrument, sketching outlines of the invisible. Every bending of light, every rotation curve, every temperature profile of cluster gas adds a stroke to that cosmic portrait. Piece by piece, the hidden mass of the universe emerges not as speculation, but as a measurable, quantifiable reality. Yet the tools do more than confirm the presence of unseen matter. They also map its distribution, showing where it gathers and how it shapes cosmic evolution. These measurements reveal a universe dominated by invisible structures, a framework that guides the formation of galaxies and clusters. Though dark matter remains elusive in every other sense, its gravitational fingerprints are everywhere, etched across billions of light years. In learning how to measure what cannot be seen, astronomers have discovered that darkness does not mean absence. It means influence without illumination, presence without glowing form. As the methods become more precise and the observations more far-reaching, the universe grows both clearer and more mysterious. For even though we can map the invisible, we still cannot touch it, taste it, or detect it directly. We can measure its gravity, but not its identity. And so the next question becomes inevitable. If the unseen mass is real, then what is it made of? Before moving toward that question, scientists first needed to remove the simplest possibilities. If something familiar could explain the invisible mass, it must be tested. And if it failed, then the mystery would deepen, guiding astronomers toward a new category of matter entirely. The challenge of measuring what cannot be seen forces astronomers to rely on signals that are almost impossibly delicate. Yet those faint imprints contain the architecture of the cosmos. Weak lensing distortions barely alter the shapes of background galaxies, yet when collected across tens of thousands of observations, they reveal sweeping contours of mass that no telescope could capture through light alone. These contours resemble a shadow cast not by illumination, but by gravity itself, a silent indication of where the unseen matter gathers and how it sculpts the space around it. In many ways, weak lensing is like listening for the rhythm of a heartbeat through layers of distance and noise. The signal is soft, but the universe repeats it with perfect consistency. When the Hubble Space Telescope first produced high-resolution weak lensing maps, astronomers were startled by how clearly the patterns emerged. Large regions of sky, once thought to be nearly empty, revealed huge concentrations of mass woven through them. These structures did not match the locations of stars or gas, but formed their own sprawling networks. This discovery strengthened the understanding that galaxies are not isolated islands drifting in the dark. They are anchored within immense halos and connected through strands of invisible matter stretching across cosmic distances. Without these strands, galaxies would not cluster in familiar patterns or orbit within groups as they do. The cosmic web owes its existence to these unseen gravitational channels. Yet gravitational lensing is not limited to the distant universe. Even nearby galaxies can warp the path of light. When a foreground galaxy subtly distorts the image of a more distant one, it provides a direct measure of the mass enclosed within its halo. Over time, numerous lensing studies have shown that galaxies with vastly different shapes and brightness levels still contain halos far larger than their luminous material suggests. Every spiral, every elliptical, every faint dwarf carries a gravitational envelope many times more massive than the stars within it. These envelopes do not glow, collide, or radiate. They simply bind. They hold galaxies together with a quiet authority that leaves no trace except through the curvature they impose on space. The cosmic microwave background offers a different kind of measurement. Rather than tracing mass through distortions of modern galaxies, it reveals the earliest gravitational fingerprints left shortly after the universe began to expand. Tiny variations in the temperature of this ancient light carry immense significance. They are snapshots of how matter and energy interacted when the universe was still young, long before galaxies existed. When scientists compared the observed pattern to theoretical predictions, a striking conclusion emerged. Ordinary matter could not produce the correct distribution of fluctuations. Without dark matter, the early universe would not have grown dense enough to form galaxies on the timescale observed. The existence of dark matter was written into the earliest chapters of cosmic history. These measurements became even more compelling when combined with studies of galaxy clusters. The hot gas within these clusters shines brightly in X-ray wavelengths, but its temperature and motion reveal that it must be confined by an enormous gravitational force. If the clusters contained only the visible galaxies and the hot gas, they would disperse rapidly. Instead, they remain bound, stabilized by a mass far greater than what their brightness implies. This additional mass cannot be dust or faint stars, as those possibilities have been tested and ruled out repeatedly. Something else must be present, something transparent to light, yet capable of pulling with extraordinary strength. NASA's missions have played a central role in refining these observations. Instruments designed to measure slight temperature differences, subtle distortions in galaxy shapes, and faint X-ray emissions have brought clarity to a mystery that once seemed almost intangible. These tools show that dark matter is not a theoretical invention meant to fill gaps in understanding. It is a measurable component of the universe, revealed through consistent results from entirely different methods. When multiple independent techniques point to the same conclusion, confidence grows. The unseen mass is real. Still, knowing that dark matter exists is not the same as knowing what it is. The ability to map its distribution does not explain its nature. It does not tell us what kind of particle or substance composes it, nor how it formed in the early universe. The gravitational measurements show only its presence and influence. They say nothing about its identity. This is where the search enters a more difficult phase. Before proposing new forms of matter, scientists must eliminate all conventional explanations. If known types of matter could account for the gravitational effects, there would be no need for new physics. Every possibility must be tested, no matter how unlikely. Planets, gas clouds, faint stars, stellar remnants, and even collections of compact objects were considered as candidates for the missing mass. Each hypothesis required careful examination, empirical testing, and the most precise observations available. Only after ruling out these familiar explanations could scientists justify turning toward more exotic possibilities. And so, with the tools of measurement, Sharpened and the gravitational maps unfolding across the sky, the next step in the journey demanded a difficult and rigorous task. To understand what dark matter might be, astronomers first needed to understand what it is not. The effort to measure the unseen does not end with mapping distortions in light or tracing motions within galaxies. It extends into the quiet precision of statistical analysis, into repeated observations that accumulate into clarity, and into models that must match the universe not in imagination, but in measurable detail. Each method reinforces the idea that the cosmos is shaped by something vast and invisible, and yet these measurements also reveal the importance of caution. Science is not built on single observations or dramatic anomalies. It is built on patterns that persist when tested repeatedly. Dark matter became a compelling concept because every method pointed toward a similar conclusion, each from a different angle, each using a different physical principle. Together they formed a tapestry of evidence woven across time and space. Weak gravitational lensing demands enormous statistical power. A single galaxy offers no reliable signature, but tens of thousands whisper a pattern that becomes unmistakable when combined. These patterns reveal how unseen mass stretches across large regions, shaping the arrangement of galaxies into clusters and filaments. The Roman Space Telescope will extend this capability by scanning wide fields with extraordinary detail, allowing astronomers to refine maps of dark matter with precision that earlier missions could not achieve. When its data arrives, scientists expect to trace the gravitational influence of the invisible with a clarity that borders on direct detection, even though the particles themselves remain elusive. The cosmic microwave background adds ancient confirmation to this modern imaging. Tiny temperature variations, measured with remarkable accuracy by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck Observatory, show that dark matter shaped the early universe long before stars existed. The patterns in the microwave background reveal the density of matter at that time, both ordinary and dark. These patterns are like fingerprints left on a smooth surface, etched by the gravitational pull of matter as it guided early fluctuations into the seeds of future galaxies. Without dark matter providing additional gravitational influence, the fluctuations would have grown too slowly, and the universe would lack the structure we see today. The evidence is encoded in a radiation field older than any star, a quiet confirmation from the dawn of time. At more local scales, clusters of galaxies offer a laboratory where gravity becomes the defining tool for measurement. When astronomers measure the speeds of galaxies swirling within a cluster, they find that the luminous matter cannot provide enough gravitational pull to keep the system together. The galaxies move too quickly, the gas grows too hot, and the gravitational field too deep for ordinary matter to explain. X-ray observations strengthen this argument. The hot gas that fills a cluster is so energetic that it would disperse unless held down by a massive gravitational well. Once again, that well is far deeper than the visible matter can provide. These independent methods intersect to form a consistent picture. The unseen mass is not a small correction. It dominates. It outweighs ordinary matter by a large factor and shapes the evolution of cosmic structure from the earliest times to the present day. Through lensing, through the cosmic microwave background, through cluster dynamics, and through orbital motion, astronomers can outline the invisible with surprising precision. The maps they construct do not show stars or glowing gas. They show contours of gravity itself, revealing where mass must lie to explain the motions and distortions visible across the sky. The striking part of this process is that none of these techniques require inventing speculative physics. They rely on well-established principles. General relativity predicts the bending of light, and observations match that prediction. Newtonian dynamics and Einsteinian gravity predict the binding forces required to hold clusters together, and the observed motions confirm the need for unseen mass. Thermodynamics predicts the behavior of hot gas, and X-ray measurements align with these expectations. Every physical law involved is known and tested. The mystery arises not from the failure of theory, but from the absence of sufficient visible matter, to satisfy those theories. This is why the search gained credibility. Dark matter was not proposed to explain a single observation. It emerged from a growing collection of measurements that consistently pointed toward a common answer. The invisible mass is there because gravity demands it. Without it, the motions, temperatures, and distortions observed throughout the cosmos would collapse into contradiction. Still, the ability to measure the unseen does not solve the deeper puzzle of what the unseen actually is. Mapping its shape reveals its influence, but not its identity. It is like hearing footsteps behind a closed door, knowing someone is there, but not knowing who. Dark matter behaves like matter in that it exerts gravity, yet it interacts so little with ordinary particles that it leaves no trail of light or heat. It neither glows nor scatters, it simply pulls, and so the scientific process moves forward with discipline. Before proposing exotic particles or unknown forms of matter, every familiar explanation must be ruled out. If planets, brown dwarfs, cold gas clouds, or faint stars could account for the missing mass, that solution would be simpler. Familiar matter would require no new physics, but each possibility must be tested with care. Only when the known has been exhausted can the unknown be considered with confidence. This leads the journey to its next essential step. If dark matter cannot be seen, and if it cannot be detected directly, then its presence must be confirmed by eliminating every alternative explanation that fails to account for the gravitational evidence. Only by closing the door on the familiar can astronomers justify opening the door to the unfamiliar. The search for dark matter does not begin with imagination. It begins with discipline. Before scientists can propose new forms of matter or explore unfamiliar physics, they must exhaust every possibility allowed by what is already known. This process is slow, meticulous, and sometimes frustrating because it forces researchers to consider possibilities that seem unlikely from the start. But science demands rigor. If the missing mass of the universe could be explained by ordinary matter in any hidden form, then there would be no need for a new category of cosmic substance. The first task, therefore, was to look carefully at everything familiar and ask a simple but profound question. Could this account for the gravitational forces observed across the universe? The earliest attempts to solve the mass discrepancy turned toward objects too faint to detect easily. Stars come in a wide range of brightness levels, and many are dim enough to escape detection with older instruments. Perhaps the galaxies were filled with large numbers of faint stars that contributed mass without contributing much light. Brown dwarfs, white dwarfs, neutron stars, or black holes formed from collapsed stars were also considered. Each of these is massive, compact, and often undetectable except under special conditions. If galaxies contained vast populations of such objects, the missing mass could, in principle, be ordinary matter in a hard-to-observe form. This category of potential explanations became known as massive astrophysical compact halo objects, a name created not to describe what they were, but to describe what they might do. They could remain hidden while providing gravitational pull. To test this idea, astronomers needed a method to detect faint or compact objects indirectly. The solution came from gravitational microlensing. When a compact object passes in front of a distant star, its gravity briefly magnifies the star's brightness. The event is subtle, yet measurable, and it provides a way to count how many unseen objects lie between Earth and distant regions of the galaxy. Large microlensing surveys began scanning the sky for these brief twinkles of magnification. If compact objects made up a significant portion of the galaxy's missing mass, such events should occur frequently. But the surveys found only a handful, far too few to account for the gravitational effects observed. These results placed strict limits on how many faint stars, brown dwarfs, and stellar remnants could exist. Though some compact objects certainly populate the galaxy, they are nowhere near numerous enough to explain the unseen mass implied by rotation curves and cluster dynamics. Another possibility involved cold gas clouds, which can remain invisible if they do not emit light, and if they absorb only weakly in certain wavelengths. But cold gas cannot remain undetected across all spectra. It affects radio signals, infrared observations, and molecular line emissions. Detailed surveys have mapped these contributions, and they consistently fall short of the mass required. Even if astronomers included every plausible cold cloud and every dust-filled region, the total mass still lagged far behind what gravitational measurements demanded. Dust itself offers no solution. Though widespread in galaxies, dust is extremely low in mass compared to stars and gas. It can dim light, but cannot contribute meaningfully to the gravitational structure of galaxies or clusters. Dust obscuration once led to the belief that some mass might be hidden behind cosmic curtains. But when infrared instruments revealed the contents of these obscured regions, no significant reservoirs of mass appeared. Scientists also considered whether black holes of primordial origin could offer an answer. These hypothetical objects, formed in the earliest moments after the universe began to expand, might have persisted into the present. If they were numerous and of specific masses, they could in theory account for some portion of the missing mass. But primordial black holes leave distinct signatures. They bend light, disturb the cosmic microwave background, and influence the distribution of matter in characteristic ways. Observations found no evidence that large populations of such objects existed at the necessary scales. The cosmic microwave background, in particular, places strong limits on how much primordial black hole mass could exist without disrupting the early development of the universe's temperature fluctuations. Those limits remove primordial black holes as a primary explanation. Even more powerful constraints come from Big Bang nucleosynthesis. In the early universe, conditions were just right for the formation of light elements such as hydrogen, helium, and small amounts of lithium. The abundance of these elements provides a precise measure of how much ordinary matter existed at that time. The observed ratios match the predictions of known physics almost perfectly. But they also reveal that ordinary matter is only a small fraction of the total mass of the universe. There is simply not enough baryonic matter allowed by the physics of the early universe to account for the gravitational effects observed today. This conclusion holds regardless of where the matter might hide. The universe never contained enough ordinary mass to explain what astronomers detect through gravitational measurements. Piece by piece, familiar explanations fell away. Faint stars could not solve the mystery. Cold gas clouds could not. Dust could not. Stellar remnants could not. Primordial black holes could not. Big Bang nucleosynthesis closed the door on most baryonic solutions entirely. The gravitational evidence remained, persistent and undeniable, while the known categories of matter proved inadequate to explain it. What was left was not speculation, but necessity. If the missing mass could not be ordinary matter, then it must be something else. This process of elimination did more than reject familiar possibilities. It strengthened the case for dark matter by showing that no conventional explanation could match the full set of observations. The universe was behaving as though a new type of matter existed, one that interacted very weakly with light and ordinary particles, but responded clearly to gravity. Without such a component, the gravitational architecture of galaxies and clusters could not be understood. Still, the elimination of the known is not the end of the journey. It is the beginning. With the familiar dismissed, scientists could finally turn their attention toward deeper possibilities. A new candidate for the unseen mass needed to be something stable, abundant, and gravitationally significant. It needed to align with observations from the cosmic microwave background, gravitational lensing, cluster dynamics, and galaxy rotation curves. It needed to fit within the framework of established physics, while extending beyond what is currently detected. And so the search moves from what dark matter is not to what it might be. Astronomers must now explore the realm of candidate particles, each grounded in real physical theories, each tested through experiments and observations, each offering a possible answer to the universe's missing mass. The task of ruling out the familiar demanded more than broad arguments or sweeping statements. It required direct confrontation with each candidate explanation, examining its behavior and comparing it with what the universe reveals through observation. Even the simplest ideas needed careful scrutiny. For instance, some researchers once wondered whether the missing mass might lie in enormous populations of planets drifting freely through interstellar space. Such rogue planets, unlit by any star, would shine only faintly in infrared wavelengths and would be extremely difficult to detect individually. If trillions of such objects existed, they could in theory provide additional gravitational pull. But the universe does not allow such possibilities to accumulate unnoticed. Rogue planets and small substellar bodies leave footprints through microlensing, through their gravitational influence on surrounding material, and through the thermal emissions that large populations would produce. Surveys conducted across years of observation place tight limits on how many of these objects could exist, and the limits fall far below the mass required to explain galactic rotation curves. Even if every undetected planet in the Milky Way were counted, the total mass would still be too small. The missing mass was simply too vast. Similar reasoning applies to brown dwarfs, objects too small to ignite sustained nuclear fusion, but still massive enough to influence their surroundings. These faint bodies emit primarily in infrared wavelengths, and early speculation suggested that galaxies might hide immense swarms of them. But deep infrared surveys conducted from space and ground observatories found nothing close to the necessary abundance. Brown dwarfs do exist, but their population is modest. They cannot explain the gravitational structures seen on scales of galaxies or clusters. White dwarfs, neutron stars, and stellar mass black holes also fall short. These compact remnants form in the depths of stars and contribute exotic beauty to the universe, but their numbers are strictly limited by the star formation history of each galaxy. They cannot appear from nowhere. Their abundance is constrained by the amount of gas available to form stars, and by the timescales over which stars evolve. If galaxies were filled with vast populations of such remnants, their chemical signatures would leave unmistakable markers. Heavy elements forged in earlier generations of stars would become overabundant, disrupting the delicate patterns observed in galactic chemistry. But measurements show nothing of the sort. The chemical makeup of galaxies aligns with known star formation rates, leaving no room for hidden populations of stellar remnants large enough to solve the mass discrepancy. After faint stars and compact objects were ruled out, scientists turned their attention to the possibility of dark clouds made of cold molecular gas. Unlike stars, such clouds emit little or no light. They could, in principle, accumulate in large quantities without attracting much attention. But molecular gas interacts strongly with radiation at specific frequencies. It absorbs and re-emits light in recognizable spectral lines, especially in the radio and millimeter ranges. When observatories mapped these signals, they found that cold gas is present, but not nearly in the quantities required to explain dark matter. The universe hosts no vast oceans of hidden gas waiting to provide the missing mass. Dust clouds invite a similar scrutiny. Dust can obscure starlight and create the illusion of empty space, but its mass is tiny compared to that of stars and gas. Even if dust filled every dark region of the galaxy, its total contribution would be negligible. Dust dims the cosmos but does not weigh it down. Some researchers also examined whether cosmic rays or exotic forms of plasma could provide additional mass, but these forms of energy interact strongly with magnetic fields and radiation. They do not linger quietly and invisibly. They produce emissions that can be measured, mapped, and quantified. All such attempts ended with the same conclusion. These components exist, but their contributions are too small or too inconsistent to account for the gravitational effects seen across galaxies and clusters. Perhaps the most intriguing familiar candidate once considered was the primordial black hole. Born not from the collapse of stars, but from density fluctuations in the very early universe, these objects could, in theory, range from microscopic scales to enormous masses. If the infant universe produced enough of them, they could seed the gravitational structures we see today. But primordial black holes are constrained by multiple lines of evidence. Their gravitational lensing effects would distort light from distant stars more frequently than observed. Their presence in large numbers would alter the pattern of temperature fluctuations in the cosmic microwave background. They would also influence the stability of binary star systems and disrupt the distribution of matter in ways inconsistent with surveys. In each case, observations showed limits far below what would be required for primordial black holes to make up the unseen mass. Then came the most decisive constraint of all, the one written into the chemistry of the universe itself. Big Bang nucleosynthesis describes how hydrogen, helium, and traces of lithium formed in the first few minutes after the universe began to expand. The ratios of these elements depend critically on the amount of ordinary matter present at that time. Observations match the theoretical predictions with extraordinary accuracy, leaving little room for additional baryonic matter. The universe does not contain enough ordinary matter to account for the gravitational forces observed. This fact alone eliminates all familiar options in one stroke. The missing mass cannot be made of baryons. By the time these constraints accumulated, the evidence had sculpted a clear and unforgiving shape. The unseen mass is not planets, not stars, not gas, not dust, not stellar remnants, and not primordial black holes. The universe has no reservoir of ordinary matter waiting to be discovered. The missing mass must be something fundamentally different, something that interacts weakly with light, does not participate in nuclear fusion, and forms a gravitational skeleton beneath the visible structures of galaxies and clusters. This conclusion does not arise from speculation, but from the slow and steady closing of doors. Each familiar possibility was given every chance to succeed. Each was tested against detailed observations and established physics. Each failed. Dark matter emerges not because astronomers wished for it, but because the universe left no other explanation consistent with the evidence. With the known ruled out, science is free to explore the unknown, and so the search turns toward new forms of matter. Candidates grounded in particle physics begin to take shape, each offering a way to account for the unseen gravitational influence. Some arise from attempts to understand the symmetry of forces. Others emerge from the search for solutions to long-standing problems in fundamental physics. Each carries a different story, a different origin, and a different signature that astronomers hope to detect. The exclusion of ordinary matter was not a philosophical shift, it was a mathematical one. Each failed explanation tightened the bounds on what dark matter could be, reducing the space of possibilities until only unfamiliar answers remained. Astronomers did not leap to exotic theories. They were pushed there by the weight of evidence. The universe itself demanded that something new existed, something that did not glow or absorb light, yet exerted a steady gravitational pull across billions of light years. As these constraints accumulated, the search transformed from ruling out old ideas to constructing a framework for what the unseen mass must be like if it truly exists. By this point, scientists had learned several key things about dark matter. First, it had to be stable over cosmic time. The universe is roughly 13,800,000,000 years old, and the unseen mass has been shaping cosmic structure since the earliest moments. If dark matter decayed quickly or transformed into radiation, the universe would look profoundly different. The gravitational scaffolding observed today would never have formed. Second, dark matter must not interact strongly with light. If it did, we would have detected it through absorption, scattering, or emission long ago. Third, dark matter cannot clump like ordinary baryonic matter does. Gas clouds collapse into stars because they can radiate energy away and cool. Dark matter does not radiate, so it remains more diffuse, forming halos rather than compact structures. Fourth, its total mass must exceed that of ordinary matter by a wide margin. The universe simply contains far more unseen mass than luminous mass. These principles, tested repeatedly through observation, created boundaries that any viable explanation must satisfy. Scientists now knew what dark matter could not be. They also knew what it must be like if it existed. This transition marked a turning point in the search. Once the familiar was excluded, particle physics offered a set of possibilities that could fill the gravitational role without violating empirical constraints. But before entering that world of candidate particles, it is important to see how thoroughly ordinary explanations had been tested and discarded. The contrast illustrates the strength of the evidence. For instance, consider again the idea of faint stars. If galaxies contained enormous populations of small, dim stars, their collective mass could add up to a significant amount. But star formation follows predictable physical laws. It produces a distribution of star sizes known as the initial mass function. Observations confirm that the universe simply does not produce stars in the numbers or sizes required to account for dark matter. No hidden population of low-mass stars exists, because their formation would require gas clouds far larger than those observed. The chemistry of galaxies also limits how many old stars could have formed in earlier epochs. Even unseen stars leave signatures that we do not find. Cold gas also fails profoundly. Gas cools, collapses, compresses, and forms stars. The universe does not allow limitless quantities of gas to remain cold and hidden. If enough gas existed to explain the missing mass, star formation rates would skyrocket, flooding galaxies with new stars and altering their chemical composition dramatically. Observations show no such excess. The stars we see today correspond closely to the amount of gas observed, not to some invisible reservoir that vanished without a trace. Even if astronomers imagined a universe filled with vast clouds of frozen hydrogen, the physics of Big Bang nucleosynthesis would forbid it. The early universe produced a precise amount of hydrogen and helium that we can measure today. That amount reflects the total quantity of baryonic matter. There is no room in the allowed budget for an enormous, unseen supply of conventional matter. Thermal behavior offers yet another decisive argument. Ordinary matter has temperature. It warms, cools, radiates energy, absorbs heat, and participates in countless interactions that leave evidence behind. Dark matter does none of this. It sits quietly in halos, unaffected by mechanisms that would cause ordinary matter to collapse or heat up. If the missing mass were made of baryonic material, we would detect its temperature or its radiation in some way. Yet across the entire spectrum, from radio waves to gamma rays, the universe offers no sign of such interactions. Even gravity itself betrays the absence of ordinary solutions. In galaxy clusters, the mass needed to confine hot X-ray emitting gas is far greater than what baryonic matter could provide. If the missing mass were baryonic, its density would be high enough to influence the cooling of the gas, but the observed cooling rates do not match what such matter would produce. Invisible matter that behaves like ordinary matter simply does not exist on the scales required. By the time these arguments reached their full weight, the dismissal of familiar matter was not a hypothesis. It was a conclusion. Every test designed to reveal hidden baryonic mass had failed, yet the gravitational evidence remained constant and insistent. Something was out there, something that bends light through gravitational lensing, holds galaxies together, anchors clusters, and allows the cosmic web to form. Something that fits none of the categories of known matter. This realization opened the door to a new chapter in physics. The missing mass must consist of particles or fields that do not fit into the standard picture of baryonic matter. These particles must interact weakly with light, remain stable across cosmic time, and be abundant enough to shape large-scale structure. They must fit theoretical frameworks without contradicting any observational constraint. Such candidates did exist in the realm of particle physics, though none had yet been confirmed experimentally. Their existence was plausible, their behavior consistent with known laws, and their signatures faint enough to escape detection. Thus, after the long and rigorous elimination of everything ordinary, scientists arrived at a boundary where the known ends and the unknown begins. To proceed, they had to explore the candidate particles that might explain the invisible, mass. These particles are not speculative fantasies. They arise naturally in theories that address unresolved problems in physics. They offer mechanisms that align with the gravitational behavior observed throughout the cosmos. They are supported by ongoing experiments, though none have been found. The path forward leads into that territory, where science seeks not to discard known physics, but to extend it just enough to describe the unseen. Having closed the door on what dark matter is not, we now turn toward what it might be. The universe had already spoken through its motions and distortions. It had shown where the unseen mass lies, how it stretches across galaxies, and how it binds cosmic structures together. But after eliminating every familiar explanation, astronomers and physicists found themselves facing a profound question. If dark matter is not made of ordinary matter in any hidden form, then what kind of substance could permeate the cosmos so silently and yet so powerfully? The answer would not come from the study of stars or clusters alone. It would require entering the realm of particle physics, where the smallest constituents of matter reveal possibilities far stranger and more delicate than anything visible in the night sky. Particle physics is built on the idea that the universe is composed of elementary particles, each with its own mass, charge, and set of interactions. Most of the particles we know are described by the Standard Model, a remarkably successful theory that explains how quarks, electrons, neutrinos, and photons behave. But the Standard Model does not explain everything. It leaves several deep puzzles unresolved, puzzles that hint at the existence of new particles beyond the familiar ones. Dark matter may be part of that unseen family. One of the earliest and most compelling candidates is the weakly interacting massive particle. Its name reflects its defining characteristics. It is massive enough to generate significant gravitational pull, yet it interacts so weakly with ordinary matter that it passes through stars, planets, and detectors almost unnoticed. The idea of such particles comes from a simple and elegant argument in cosmology known as thermal freeze-out. In the early universe, temperatures were so high that particles and antiparticles collided constantly, forming and annihilating one another in a dynamic equilibrium. As the universe expanded and cooled, that equilibrium broke down. Particles with certain properties would stop annihilating efficiently, leaving behind a stable population that persisted into the present. If a particle had a mass and interaction rate within a particular range, the leftover abundance would match the amount of dark matter inferred from observations. This coincidence is sometimes called the thermal miracle, because it suggests that dark matter could arise naturally from processes already known to operate in the early universe. It does not require exotic assumptions. It simply requires the existence of a particle with the right mass and the right weak interactions. This idea gained traction because it fits neatly into established theories that extend the Standard Model, offering a graceful explanation for the missing mass. Yet weakly interacting massive particles have one major complication. They have never been detected in laboratory experiments, even though many detectors operate deep underground to avoid interference from cosmic rays. These detectors attempt to measure the tiny recoil produced when a weakly interacting particle collides with an atomic nucleus. Though such collisions are rare, they should occur occasionally if these particles fill the universe. Experiments have become increasingly sensitive, ruling out large regions of possible masses and interaction strengths. The absence of detection does not disprove their existence, but it narrows the window of possibilities. Another leading candidate emerged from an entirely different problem in physics, the strong charge parity problem. In certain theories of particle interactions, the strong nuclear force should behave in a way that violates a type of symmetry known as charge parity symmetry. Yet no such violation has ever been observed. To resolve this discrepancy, physicists introduced a new kind of particle, the axion, named for its ability to clean up the theoretical framework, much like a cleanser. Axions would be extremely light, electrically neutral, and produced abundantly in the early universe. They would also interact so weakly with light that they could slip through space without scattering or glowing, making them nearly impossible to detect directly. Despite their elusiveness, axions offer an appealing explanation for dark matter because they emerge naturally from a solution to a real theoretical puzzle. Unlike weakly interacting massive particles, which require specific properties to match the thermal freeze-out abundance, axions carry a theoretical motivation independent of dark matter. Their existence solves a symmetry problem, and their properties make them excellent dark matter candidates almost by accident. Experiments designed to detect axions often attempt to convert them into photons using strong magnetic fields, hoping to capture the faint signals that such conversions might produce. Though no definitive detection has been made, experimental efforts continue to refine their sensitivity, exploring the possible range of axion masses with increasing precision. A third candidate arises from an extension of the neutrino family. Neutrinos are elementary particles with very small masses that interact only through the weak nuclear force. They pass through matter effortlessly, and billions of them stream through every square centimeter of space each second, barely interacting with anything at all. But neutrinos in the standard model are too light and too fast-moving to form the gravitational structures seen across the universe. To act as dark matter, a neutrino-like particle would need to be heavier and would need to move more slowly. This possibility leads to the idea of the sterile neutrino, a particle that does not interact through any force except gravity. If sterile neutrinos exist, they could account for at least part of the dark matter. Observations of faint X-ray signals in certain galaxies and clusters have inspired debate over whether they might originate from the decay of such particles. However, the evidence remains uncertain, and the interpretation of these signals is still under rigorous scrutiny. These three candidates represent the leading possibilities in the search for the unseen mass. Each arises from well-motivated physics. Each offers a different mechanism by which the universe could carry the weight of its invisible component. None contradicts existing observations, and each possesses unique features that ongoing experiments attempt to explore. Yet none has been confirmed. The search continues, not because scientists lack options, but because the universe reveals so little about what dark matter actually is. The gravitational evidence is clear, but the particle identity remains hidden behind a veil of weak interactions and subtle signatures. Still, the search does not rely on theory alone. NASA's instruments play a crucial role in testing these possibilities from the perspective of astronomy. Space-based observatories detect high-energy photons, map regions of hot gas, and study the faint glow of distant structures where potential signals from dark matter might appear. Gamma rays, X-rays, and subtle emission lines offer clues to whether particles might annihilate, decay, or interact in ways detectable from Earth. These observations provide constraints that guide experimental physics, shaping the parameter space where viable candidates may exist. As these worlds of particle physics and astronomy converge, the search becomes more focused. Dark matter must be something real, something with mass, something that influences the universe gravitationally. The theories that survive this scrutiny must align with every observation, every map, every experiment. In this merging of cosmic measurement and particle theory, the universe may eventually reveal the identity of its unseen majority. Weakly interacting massive particles gained early support because they seemed so natural within the thermal history of the young universe. If particles of this kind existed, they would have formed in enormous quantities when temperatures were unimaginably high. As the universe expanded and cooled, their annihilation reactions would have slowed. Eventually, the expansion would have separated them faster than they could collide, leaving behind a stable population. This is the idea of thermal freeze-out, a process that requires no fine-tuning and no exotic assumptions. It simply follows from the physics of particles in a dense, hot environment. If the mass and interaction strength of these particles fall within a certain range, the leftover abundance matches the amount of dark matter inferred from cosmology. This remarkable alignment between theory and observation made weakly interacting massive particles one of the most compelling candidates for decades. But cosmic elegance does not guarantee existence. Experiments designed to detect these particles attempt to observe the minuscule energy deposited when one of them collides with an atomic nucleus. The detectors are buried deep underground to shield them from cosmic rays and natural background noise. They use ultra-pure materials and cryogenic temperatures to prevent contamination by ordinary radiation. With each passing year, these detectors grow more sensitive, narrowing the range of possible masses and interaction strengths. Dozens of experiments have reported null results. The absence of detection is not evidence against their existence, but it pushes weakly interacting massive particles into smaller corners of parameter space. If they exist, they must be lighter, heavier, or more weakly interacting than earlier models predicted. This process is a reminder of how science advances. Ideas are not discarded lightly. They are tested, refined, constrained, and retested. An undetected particle is not disproven. It simply must hide more effectively or behave differently than expected. Yet doubts grow when experiments remain silent. The universe does not reveal its secrets easily. Axions present a very different profile. While weakly interacting massive particles were born from cosmology, axions were born from the structure of the strong nuclear force. The equations that describe this force contain a parameter that should create a violation of charge parity symmetry, but no such violation has ever been observed. The lack of this effect presents a deep theoretical puzzle. Axions offer a graceful solution. If they exist, they naturally suppress the unwanted symmetry violation, aligning theory with observation. Their existence is not required by dark matter, but by the internal consistency of the strong nuclear force. Their properties then make them perfect dark matter candidates by coincidence. Axions are extraordinarily light, far lighter than electrons or neutrinos. They do not interact strongly with other particles, making them nearly transparent to the universe. Experiments that search for axions often rely on their ability to convert into photons in the presence of strong magnetic fields. Instruments built for this purpose resemble resonant cavities, where scientists listen for faint electromagnetic signals that might reveal the presence of axions swirling through the Milky Way. Thus far, these experiments have not confirmed their existence, but they continue to probe new regions of mass and coupling strength. Axions could be so light and so weakly interacting that current detectors barely scratch the surface of possible values. The search may take decades, but the theoretical motivation keeps it alive. Sterile neutrinos add yet another dimension to the search. Ordinary neutrinos interact only through the weak nuclear force and gravity. They are some of the most elusive particles in nature. Sterile neutrinos, if they exist, would interact even less. They would feel no force but gravity. These particles arise naturally in certain extensions of the Standard Model, especially those attempting to explain why ordinary neutrinos have such small masses. If sterile neutrinos have masses in the right range, they could serve as dark matter. Unlike weakly interacting massive particles, which would have been cold and slow-moving shortly after formation, sterile neutrinos might have been warm, moving with moderate speeds. This difference affects the formation of galaxies, smoothing out the smallest structures while preserving larger ones. Observations show that the universe contains rich structure on small scales, suggesting that dark matter must be mostly cold. Yet a small component of warm material is not excluded. This leaves sterile neutrinos in a complex but intriguing position. Occasionally, astronomers have detected faint emission lines in X-ray observations that spark debate. One such line has appeared around 3.5 kilo electron volts in certain galaxies and clusters. Some researchers argue that it could result from the decay of sterile neutrinos, producing photons with that energy. Others explain it through more conventional atomic processes. The evidence remains uncertain, and the debate continues, showing how delicately the universe whispers its secrets. science must tread carefully, avoiding both overinterpretation and dismissiveness. A signal must be confirmed across multiple instruments and contexts before it is accepted. Until then, the possibility remains open. NASA's contributions to this field extend beyond mapping lensing or measuring cosmic background fluctuations. Observatories such as the Fermi Gamma Ray Space Telescope, Chandra, and XMM Newton search for indirect signals that certain dark matter particles might produce. If weakly interacting massive particles annihilate, they could emit gamma rays. If sterile neutrinos decay, they might release X-rays. These observations offer glimpses into the potential signatures of dark matter, guiding experimentalists toward promising regions of parameter space. Though none of these findings count as definitive evidence, they narrow the search and refine the theories. As each candidate is tested, the space of possibilities becomes more structured. Dark matter cannot be anything. It must be something that fits the tapestry of cosmic evidence. Theories that attempt to explain dark matter must obey gravitational data, cosmic microwave background measurements, and the distribution of galaxies. They must align with laboratory experiments and remain consistent with thermodynamic principles. This discipline is what keeps the field anchored, even when the subject itself remains invisible. The beauty of this pursuit lies in the harmony between physics on the smallest scales and the largest. Elementary particles influence the formation of galaxies. The early universe sets the boundaries for what particles may exist today. Astronomy and particle physics become intertwined, each providing insights the other cannot. Dark matter lives at that intersection, demanding a unification of knowledge across disciplines. The search continues with persistence because the evidence demands it. Something fills the halos of galaxies, anchors galaxy clusters, and shapes the cosmic web. Something beyond ordinary matter dominates the mass of the universe. As long as that truth remains unexplained, the journey continues, guiding scientists deeper into the landscape of particle theory in search of the unseen. The deeper the search moved into the realm of particle candidates, the clearer it became that dark matter was not an isolated puzzle. It was entangled with broader questions about the foundations of physics. Every leading candidate emerged not from speculation, but from attempts to solve independent problems in cosmology or particle theory. This convergence offered reassurance. If dark matter belonged to a family of particles already motivated by other unresolved mysteries, then the invisible mass might be part of a structure waiting to be discovered rather than an anomaly standing alone. Weakly interacting massive particles, for instance, arise naturally in theories that attempt to unify the forces of nature at high energies. These theories suggest that at extreme temperatures, such as those present shortly after the birth of the universe, the fundamental forces may merge. When physicists construct mathematical frameworks to describe this unification, new particles often emerge with properties that match those needed for dark matter. Though these models remain unproven, they demonstrate that the idea of weakly interacting massive particles is rooted in the search for deeper symmetries, not merely invented to explain missing mass. Axions also reflect this convergence of problems. Their origin lies in the effort to preserve the symmetry of the strong nuclear force, a symmetry whose violation should be evident but is not. If axions exist, they not only solve this puzzle, but also provide a reservoir of mass that formed naturally in the early universe. They require no adjustments or artificial tuning to match cosmological observations. Their abundance arises directly from their theoretical role, offering a graceful and efficient explanation for why the universe contains so much invisible matter. Sterile neutrinos, on the other hand, form part of the effort to understand the masses of ordinary neutrinos. The fact that neutrinos have mass at all was a significant discovery that required new physics beyond the standard model. Sterile neutrinos extend this framework while simultaneously offering a potential dark matter candidate. Their properties influence the formation of cosmic structure in ways that can be tested, providing a bridge between astrophysics and particle theory. Yet the existence of compelling candidates does not relieve scientists from the obligation to test them relentlessly. Experiments designed to detect weakly interacting massive particles operate with sensitivity levels unimaginable to earlier generations. They listen for the faint energy deposited by a collision so rare that it might occur only once in years. Some detectors rely on cryogenic crystals. Others use liquid xenon kept at temperatures where even the slightest motion can be observed. Despite the sophistication of these instruments, no confirmed detection has yet been made. With every null result, the parameter space narrows, and the remaining possibilities require particles that are either more weakly interacting or exist in mass ranges more difficult to probe. Axion detection experiments face their own challenges. Because axions interact so feebly, the signals they produce are not only faint, but also frequency dependent, requiring instruments tuned to specific ranges. As researchers adjust their searches across different mass windows, they map out the terrain of possibility with slow and methodical precision. The work is painstaking, but the potential reward is profound. A confirmed axion signal would not only identify dark matter, but also solve a major puzzle in the strong nuclear force. Sterile neutrinos introduce a different form of difficulty. Because they interact only through gravity, they cannot be detected through traditional particle interactions. Their signatures must come from indirect effects, such as the potential emission of X-rays when they decay. The debated 3.5 kilo electron-volt emission line exemplifies both the promise and the challenge of studying such particles. If the line comes from sterile neutrino decay, it would indicate a particle mass compatible with certain dark matter models. But if the line is produced by known atomic processes, then the signal is not evidence of new physics. Competing interpretations highlight the need for clarity and caution. Observations must be replicated across different instruments, regions of the sky, and astrophysical environments before any conclusion can be drawn. NASA's observatories contribute significantly to this process by surveying the universe across multiple wavelengths. Fermi examines gamma rays that could arise from the annihilation of weakly interacting massive particles. Chandra and XMM Newton observe X-ray emissions that might reveal sterile neutrino decay or other forms of faint particle interactions. These missions do not seek dark matter directly, but search for the secondary signatures that its particles might produce. Though none of these signals has yet achieved the level of certainty required for scientific acceptance, the constraints they provide shape the theories that follow. Across all these efforts, one theme remains constant. Dark matter must reveal itself through gravity, yet gravity tells nothing about the particle identity. It remains the one messenger that cannot be silenced, the single thread that connects galaxies, clusters, and the cosmic web. But gravity alone cannot distinguish between weakly interacting massive particles, axions, sterile neutrinos, or something entirely different. To understand dark matter fully, scientists must combine gravitational evidence with laboratory experiments, indirect signatures, and theoretical insights. Only through this combination can the invisible become describable. This interplay between cosmic structure and particle physics forms one of the most ambitious scientific quests of the modern era. The candidates grow narrower as constraints grow stronger, yet the mystery persists. Something massive, stable, abundant, and nearly invisible dominates the universe. The solutions presented by particle physics offer compelling possibilities, but until one is confirmed, the search remains open. And so the journey continues. The universe has shown what dark matter cannot be. It has offered glimpses of what it might be. The next phase of exploration shifts back to gravity itself, the only reliable messenger, and to the ways this messenger outlines the unseen. For even though the particle identity remains hidden, gravity has already revealed the shape and influence of the invisible mass in exquisite detail. Gravity speaks across the universe with a patience unmatched by any other force. It carries no light, no color, no whisper of charge, yet it binds galaxies across millions of light years and shapes the vast architecture of the cosmos. For dark matter, Gravity is not just one clue among many. It is the only signal that arrives reliably, the one messenger that does not fade with distance, the one interaction that reveals the presence of the unseen with absolute certainty. Every distortion of starlight, every unexpected orbital velocity, every cluster held together against the odds is a signature written in the language of curved space. To understand why gravity provides such a powerful window into dark matter, we must return to Einstein's insight that mass does not pull in the traditional sense. Instead, it shapes the geometry of space and time. Objects follow the paths carved by this geometry, moving along curves created not by forces but by the structure of space-time itself. Light, though massless, also responds to this curvature. It bends when it travels near massive objects, tracing arcs and distortions that reveal the invisible outline of gravitational fields. In this view, gravity becomes not an interaction to be measured directly, but a shape to be studied and interpreted. This interpretation allows astronomers to measure mass even when the matter itself remains dark. If space bends, something must be present to bend it. If stars orbit faster than expected, something must be adding gravitational weight. If clusters remain bound despite the enormous energy within them, something must be providing the necessary grip. Through these effects, gravity becomes a map, guiding astronomers toward the unseen. The study of orbital velocities provides one of the earliest and most compelling gravitational signatures of dark matter. In a galaxy like the Milky Way, stars orbit the galactic center at speeds determined by the enclosed mass. If only visible matter contributed to the gravitational pull, stars far from the center would move slowly. But they do not. They move with speeds that imply far more mass than telescopes reveal. This behavior is not unique to the Milky Way. Galaxies of every type show the same pattern. The rotational velocity remains nearly constant at large distances, as though the galaxy is embedded in a vast halo of unseen material. No modification of visible matter can replicate this effect across so many systems. Clusters of galaxies amplify this gravitational story. These enormous assemblies are laboratories for extreme physics. The galaxies within them move rapidly, responding to deep gravitational wells, whose depth cannot be explained by luminous mass alone. Measurements of these motions reveal that the total mass of a cluster often exceeds the visible mass by factors of several. The hot gas that fills clusters confirms this picture. It emits X-rays because it is heated to temperatures of millions of degrees. Such gas should escape the cluster unless held by an immense gravitational force. Once again, the visible matter cannot supply that force. Gravitational lensing offers perhaps the most elegant demonstration of unseen mass. When light from a distant galaxy passes near a massive cluster, space-time bends its path, distorting the image seen by observers. These distortions provide a direct measure of the total mass along the line of sight. When mass maps created by lensing are compared to maps of visible matter, the discrepancy is striking. The gravitational mass is far greater, and its distribution often extends beyond the luminous regions. In some cases, such as colliding clusters, the separation between luminous matter and gravitational mass becomes unmistakable. The mass revealed by lensing travels differently than the hot gas, leaving no doubt that an unseen component dominates the cluster's gravitational landscape. NASA's satellites have played a crucial role in refining these measurements. Instruments such as the Hubble Space Telescope capture weak lensing signals across wide fields, revealing subtle distortions in the shapes of distant galaxies. These distortions allow astronomers to reconstruct mass distributions with remarkable clarity. The upcoming Roman Space Telescope will extend this capability even further, mapping the dark matter of the cosmos with unprecedented precision, tracing the invisible with sensitivity that current instruments can only approach. Ground-based observatories contribute as well, but space offers a stability and clarity unmatched by even the finest terrestrial telescopes. Without atmospheric interference, space-based instruments can detect faint signals, measure small distortions, and observe distant galaxies with the consistency required for gravitational studies. Gravity does not weaken as light dims. It leaves its imprint even on the faintest images. This reliability is what makes gravitational lensing so powerful. But gravity does more than reveal the presence of dark matter. It also reveals its distribution. Dark matter does not collapse into stars or planets because it cannot radiate energy and cool. Instead, it forms extended halos around galaxies and clusters. These halos influence how galaxies rotate, how they merge, and how they move through space. The shapes of halos can be inferred through gravitational measurements, showing flattening, elongation, or clumping that corresponds to the large-scale structure of the universe. This gravitational scaffolding underlies the cosmic web, the vast network of filaments and voids that stretches across space. Ordinary matter falls into the gravitational wells created by dark matter, forming galaxies at the centers of halos. These galaxies then drift along filaments, merging with others and growing over time. The cosmic web is not built by light. It is built by gravity carving channels into the early universe. Without dark matter's gravitational influence, galaxies would not have formed so early or so efficiently. Even as gravity provides the clearest evidence for dark matter, it also highlights the difficulty of discovering what dark matter actually is. Gravity cannot distinguish between particles. It does not care whether the unseen mass consists of weakly interacting massive particles, axions, sterile neutrinos, or something else entirely. It reveals only the total mass and its distribution. This limitation is both a strength and a frustration. It proves dark matter exists, yet it offers no direct insight into the particle nature of the unseen. Astronomers must therefore rely on gravity as the primary tool while pursuing other methods to identify the particles themselves. Every gravitational measurement refines the constraints imposed on theoretical models. The mass distribution of galaxies, the shapes of halos, the binding of clusters, and the patterns in the cosmic microwave background all provide boundaries within which particle theories must operate. These boundaries ensure that theoretical candidates cannot be invented freely. They must align with the gravitational truth written into the universe. The more precisely astronomers measure gravitational effects, the narrower the theoretical possibilities become. With every lensing map, every orbital study, and every cluster measurement, gravity sharpens the focus on the unseen. It stands as the most reliable messenger in a universe where most of the mass does not shine, a messenger that delivers its message through curvature rather than brightness. And yet, gravity alone cannot answer the final question. It reveals where dark matter is and how much of it exists, but not what it is made of. To uncover its identity, scientists must consider whether the laws of gravity themselves might need adjustment. Before accepting dark matter as a new form of matter, some researchers propose that gravity behaves differently on large scales. Testing these ideas would become the next crucial step in understanding the invisible. Gravity is an uncompromising teacher. It reveals patterns with absolute clarity, yet it refuses to offer explanations beyond those patterns. It tells astronomers how fast stars move and how clusters hold together. It shows where mass must lie, how halos extend far beyond their luminous centers, and how galaxies trace the contours of unseen structures. But it never tells what the mass is. This limitation leaves room for doubt, and it is in that doubt that creativity once stirred. If the universe behaves as though unseen matter exists, perhaps the matter is not missing at all. Perhaps the laws of gravity change under certain conditions. Before accepting the existence of a new form of matter, scientists needed to consider whether the simplest explanation might involve modifying the familiar rather than inventing the unfamiliar. To understand why gravity could not be dismissed lightly, one must appreciate how deeply rooted it is in both observation and theory. Newton's formulation of gravity guided human understanding for centuries. It explained the orbital motions of planets around the Sun, the return of comets, the tides of the oceans, and the trajectories of falling objects. It was elegant, predictable, and remarkably precise. Later, Einstein extended this understanding with general relativity, showing that gravity arises not from a force, but from the curvature of space-time. This theory predicted phenomena Newton could not have imagined, such as the bending of starlight and the existence of black holes. General relativity has passed every experimental test with extraordinary accuracy. It describes the behavior of massive objects with a consistency unmatched by any other theory in modern physics. Yet the rotational behavior of galaxies presented a puzzle that neither Newton nor Einstein anticipated. If the laws of gravity remained unchanged at all scales, the motions of stars within galaxies should follow the distribution of visible matter. But they do not. Instead of slowing as they move outward, stars maintain high velocities far beyond the luminous boundaries. This led some researchers to propose that gravity might weaken differently at large distances, requiring a modification to the traditional laws. These ideas were not rejections of Einstein, but attempts to adjust the details in ways that might explain galactic rotation curves without invoking unseen matter. Modified gravity theories gained early attention because they offered a clean explanation for certain patterns. They attempted to describe the universe with familiar components rather than adding new ones. But gravity, though patient, is not forgiving. Any change to its behavior must be consistent across all scales, from the motion of stars within galaxies to the binding of galaxy clusters and the formation of the cosmic web. The challenge is not to adjust gravity to match one observation, but to adjust it in a way that matches all observations simultaneously. The most well-known attempt to modify gravity emerged as scientists continued to grapple with flat rotation curves. This approach, known as modified Newtonian dynamics, suggested that the behavior of gravity changes when accelerations become extremely small. Under this idea, the outer regions of galaxies would naturally exhibit higher velocities without requiring additional mass. Modified Newtonian dynamics could match rotation curves in many galaxies, giving it early appeal. But as more data accumulated, limitations became clear. The theory could not consistently explain the behavior of galaxy clusters, where the discrepancy between visible mass and gravitational pull is too large to be addressed by a simple modification. It also struggled to reproduce the patterns observed in the cosmic microwave background, which require a non-baryonic form of mass to shape early density fluctuations. Einstein's general relativity provides a more complete framework than Newton's laws, yet modifying it is far more complex. Some researchers proposed extensions of general relativity that introduced additional fields or altered the structure of space-time in subtle ways. These theories attempted to mimic the gravitational behavior produced by dark matter without requiring new particles. While certain models could reproduce specific observations, they often failed when tested against the full range of astrophysical data. Gravity leaves a consistent signature across the universe, and any deviation from its standard behavior must remain consistent with every observation. The more data scientists gathered, the more difficult it became for modified gravity theories to fit the cosmic picture without contradiction. Gravity remained honest even when researchers looked for alternatives. It revealed that the unseen mass must exist because the structure of the universe cannot form without it. The cosmic web, with its delicate filaments and vast voids, arises naturally in simulations only when dark matter is included. Without it, the universe would be smoother, lacking the rich texture observed in galaxy surveys. The cosmic microwave background provides further evidence. The pattern of temperature fluctuations requires a form of matter that does not interact with light. No modification of gravity alone can replicate these features without introducing inconsistencies. NASA's contributions to these measurements strengthened the case. Observations from space-based telescopes mapped gravitational lensing across enormous cosmic distances. These maps reveal the locations of mass directly through its curvature of space. Modified gravity theories struggle to reproduce these lensing signals without invoking something that behaves precisely like dark matter. At that point, the difference becomes semantic. If gravity must include a new component to behave correctly, that component is effectively dark matter by another name. Even observations of the Bullet cluster, a pair of colliding galaxy clusters, provided dramatic evidence. When the clusters collided, the hot gas within them slowed down due to friction, while the galaxies passed through one another more freely. Gravitational lensing revealed that most of the mass traveled with the galaxies rather than with the gas. This separation between luminous matter and gravitational mass cannot be explained by modifying gravity alone. It requires mass that interacts weakly with everything except gravity. Dark matter fits this requirement precisely. With each test and measurement, gravity made its message unmistakable. The unseen mass exists not because we wished for it, but because the universe insists on it. No modification of gravity could explain all observations simultaneously without reintroducing some form of additional mass. The simplest and most consistent explanation remains that the universe contains a new form of matter, invisible but real, silent but gravitationally powerful. Even so, the search does not end with this conclusion. Gravity reveals where dark matter lies, but it offers no insight into how it shapes the universe beyond its pull. To understand the structure of the cosmos, scientists must explore how dark matter helps form the vast network of galaxies and clusters across space. The next step is to follow the invisible scaffolding into the largest patterns the universe has ever produced. Gravity continues to guide the investigation with unwavering consistency. It draws a clear outline of the invisible, yet it also reveals how deeply the unseen matter participates in shaping the very framework of the cosmos. The more astronomers study the universe through its gravitational imprints, the more they recognize that dark matter does not merely sit within galaxies or linger around their edges. It is a structural component, a quiet architect that determines how galaxies form, how they move, and how they interact over billions of years. Gravity shows that dark matter is not an accessory to cosmic evolution. It is one of its primary drivers. When simulations of the universe are constructed using only ordinary matter and the laws of general relativity, the resulting landscapes bear little resemblance to the cosmos we observe. Galaxies do not form quickly enough. Their sizes and distributions fail to match large-scale surveys. The delicate filaments and voids that stretch across the universe do not appear. Instead, the simulations produce a smoother, less textured cosmos, lacking the intricate networks seen in astronomical data. But when dark matter is added to these simulations in the proportions suggested by gravitational measurements, the universe begins to take on its familiar form. Filaments emerge naturally. Galaxies cluster along strands of invisible mass. Voids expand between them. The simulated universe becomes a mirror of the real one. This harmony between observation and simulation strengthens the case that gravity is revealing something fundamental. Dark matter must exist not only because it solves the problem of rotational velocities or cluster dynamics, but because it is essential to the formation of cosmic structure. Without its guiding gravitational influence, the universe could not have evolved into its present state. The cosmic web is a testament to the unseen, a map drawn not by luminous matter, but by the gravitational wells carved by dark matter. The gravitational influence of dark matter also shapes the behavior of galaxies long after their initial formation. When galaxies merge, their halos interact first, creating tidal structures that precede the visible collision. These invisible halos determine how the galaxies spiral toward one another, how their stars are redistributed, and how their central black holes eventually coalesce. Even the motions of satellite galaxies orbiting larger systems reveal the presence of these halos. Observations show that small galaxies orbit in ways that require massive reservoirs of unseen matter extending far beyond the reach of their luminous components. Gravity remains precise even in these complex interactions. It shows how dark matter anchors galaxies within clusters and how clusters themselves drift within larger structures. It reveals patterns of infall, where groups of galaxies move toward denser regions of the cosmic web. It shapes the expected frequency with which galaxies collide and merge. All of these behaviors provide additional evidence that dark matter is more than a theoretical necessity. It is a physical component with consistent effects across all cosmic scales. Even gravitational lensing, one of the most powerful tools for exploring the unseen, demonstrates how dark matter moves through space, independently of ordinary matter. In some merging systems, the dark matter passes through a collision with minimal resistance, while the luminous gas lags behind, slowed by friction and heating. The mass maps reconstructed from lensing reveal this separation with striking clarity. The gravitational mass and the luminous matter do not always coincide, proving that the invisible component does not interact through the familiar processes that govern ordinary matter. It neither heats nor slows in the ways that gas and plasma do. Its interactions are limited to gravity, giving it an almost ghost-like presence. NASA's missions continue to refine this understanding by providing the most detailed gravitational maps ever produced. With each new observation, the patterns grow sharper. Weak lensing surveys reveal the distribution of mass across enormous regions of the sky. High-resolution imaging captures the subtle distortions caused by both large-scale structures and individual galaxies. These datasets feed into models that reconstruct the gravitational landscape of the universe with extraordinary detail. As the Roman Space Telescope prepares to survey vast portions of the sky with unprecedented clarity, the gravitational portrait of the cosmos will become even more precise. Through all of this evidence, a single truth emerges. Dark matter must exist as a real, physical component that shapes the universe through gravity alone. The laws of gravity need no modification when dark matter is included. They describe the motions and structures of the cosmos with remarkable fidelity. It is the matter content that was incomplete, not the laws themselves. Gravity remains a reliable messenger because it responds only to mass and energy. It cannot be fooled by brightness or obscured by dust. It simply curves space according to what exists, whether visible or not. Yet gravity, for all its reliability, brings us to the edge of its usefulness in identifying what dark matter is made of. It shows the structure, the influence, the distribution, and the mass, but it does not offer the identity. To uncover that, scientists must push beyond gravitational evidence and consider whether the laws of gravity might hide deeper subtleties, or whether something in the nature of matter itself remains undiscovered. This leads naturally into one of the most critical questions in modern astrophysics. If gravity so clearly reveals the presence of dark matter, could the laws of gravity themselves be responsible for the illusion of unseen mass? Before accepting dark matter as the full explanation, researchers needed to confront this possibility directly. The next step in the journey is to examine whether the force that has guided astronomy for centuries requires modification at the grandest scales. The mystery of dark matter grew out of gravitational evidence, and so it was only natural to ask whether gravity itself might be the part that needed revision. If the motions of stars and the binding of clusters could not be explained by the visible mass alone, perhaps the rules governing attraction on cosmic scales were subtly different from those observed in the solar system. This question did not arise from a desire to avoid the unknown, but from scientific discipline. Before introducing a new form of matter into the universe, one must be certain that no adjustment to existing laws can explain the observations. The path forward required confronting one of the oldest and most reliable theories in physics and asking whether its reach extended perfectly across all scales, or whether the universe might behave differently in its faintest and most delicate regions. The first serious attempt to modify gravity began with a simple observation. The discrepancy between predicted and measured rotational velocities in galaxies appeared strongest where accelerations were extremely small, far weaker than anything encountered in the solar system. This led to an idea both bold and elegant. Perhaps gravity behaves normally at high accelerations, but changes form at low ones. Under this proposal, called modified Newtonian dynamics, the force governing the motion of stars would increase slightly in regions of weak acceleration, flattening the rotation curves without requiring additional mass. For many spiral galaxies, this approach reproduced the observed velocities remarkably well. It fit the data with surprising accuracy across systems of different sizes and luminosities, offering a tempting alternative to unseen matter. But the universe is not composed of isolated spiral galaxies. It contains clusters, filaments, and vast tidal structures stretching across unimaginable distances. Any modification to gravity must remain valid not only in one environment, but in all of them. Modified Newtonian dynamics struggled almost immediately with galaxy clusters. The gravitational discrepancy in clusters is far larger than in individual galaxies, yet the modified acceleration could not account for the extreme motions of cluster members or the high temperatures of the hot gas permeating them. The theory required additional unseen mass to explain these systems, undermining the very reason it had been introduced. A modified law that still needed dark matter was not a solution. It was an approximation at best. More sophisticated attempts to adjust gravity emerged in the decades that followed. Some researchers sought to embed modified Newtonian dynamics within a broader relativistic framework, creating theories that preserved the curvature of spacetime but introduced new fields or altered geometric terms. These efforts aim to replicate the successes of modified Newtonian dynamics while extending its reach to cosmology. Yet even these advanced models faced challenges. They struggled to reproduce the distribution of mass inferred from gravitational lensing, especially in systems where dark and luminous matter separate spatially. They also failed to match the detailed patterns in the cosmic microwave background, patterns that require a significant non-luminous mass component in the early universe. Without such a component, the delicate fluctuations imprinted on that ancient light cannot develop into the web of galaxies observed today. The cosmic microwave background is particularly unforgiving. It records the behavior of the universe when it was still young, long before galaxies formed. The positions and magnitudes of its temperature variations depend sensitively on the amount and type of matter present. If gravity alone were responsible for the observed discrepancies, the microwave background would show a different pattern. Instead, it displays one that aligns precisely with a universe containing both ordinary matter and a substantial amount of dark matter. Modified gravity theories cannot reproduce this pattern without introducing something that behaves exactly like the unseen matter they were designed to replace. The most striking evidence comes from systems where the gravitational mass and visible mass become physically separated. The Bullet cluster, a pair of colliding galaxy clusters, provides one of the clearest examples. When the clusters passed through one another, the galaxies moved largely undisturbed, but the hot gas within them collided and slowed, accumulating between the two systems. Gravitational lensing revealed that the dominant mass traveled with the galaxies, not with the slowed gas. This separation cannot be explained through modified gravity alone. It requires mass that interacts weakly with matter and radiation, passing through collisions unhindered. Dark matter behaves in precisely this way. Gravity in this system points directly to the presence of an unseen mass component, distinct from the luminous matter. NASA and other observatories have analyzed similar systems across the cosmos, and the results remain consistent. In each case, mass traces a distribution different from the luminous gas. The gravitational field does not follow the pattern that modified gravity would predict if the luminous matter were the only contributor. Instead, it follows a pattern that demands an additional, invisible component. These repeated confirmations strengthen the case that dark matter is not an illusion created by incomplete gravitational laws, but a real substance interacting through gravity alone. Still, the pursuit of modified gravity was not wasted effort. It forced scientists to examine their assumptions, refine their measurements, and test the limits of one of physics' most successful theories. The fact that general relativity continues to match observations across such a wide range of environments speaks to its remarkable power. It bends light precisely as predicted. It governs the motions of stars, galaxies, and clusters with consistent accuracy, and when supplemented by dark matter, it reproduces the entire cosmic structure from the smallest galaxies to the largest filaments. By the time these investigations reached maturity, the verdict had become clear. While modified gravity could mimic certain galactic behaviors, it could not explain the universe as a whole. Dark matter remained the only explanation capable of matching every observation simultaneously. Gravity had once again guided astronomers toward a deeper truth, showing that the unseen mass was not a mere artifact of incomplete equations, but a fundamental component of the cosmos. The search for an alternative to dark matter continued with admirable persistence, but the universe proved more intricate than any single adjustment to gravity could capture. As astronomers explored deeper into the behavior of galaxies, clusters, and the cosmic web, each line of evidence added new layers that modified gravity theories struggled to replicate. A single phenomenon, such as a flat rotation curve, could be imitated by altering the gravitational law. But the cosmos is not built from isolated puzzles. It is a layered, interdependent structure where every observation influences another. Each test became a crossroads at which modified gravity theories diverged further from the empirical landscape. One of the most subtle challenges emerged from the way galaxies form and evolve over time. Simulations that include dark matter produce galaxies of the correct shape, size, and distribution. They generate satellite systems, spirals, dwarf galaxies, and merging structures that resemble those observed in real surveys. Modified gravity theories can match certain isolated features, but they cannot reproduce this entire evolutionary sequence without introducing inconsistencies. Galaxy formation requires gravitational potentials deeper and more extended than luminous matter alone could ever provide. Even if a modified law could mimic rotation curves, it could not recreate the conditions necessary for galaxies to assemble so early or remain stable for so long. The same is true for the formation of dwarf galaxies. These small systems are especially sensitive to gravitational effects because they possess far less luminous matter than larger galaxies. In many dwarf galaxies, the discrepancy between visible mass and required gravitational mass is even more pronounced. Modified gravity theories cannot explain the diversity of their dynamics, nor can they account for the fact that many dwarf galaxies orbit within the halos of larger systems. In simulations with dark matter, these behaviors arise naturally. Without dark matter, they become contrived, requiring adjustments that fail when tested across multiple environments. Galaxy clusters present even greater difficulties. The mass discrepancy in clusters is not modest, it is enormous. To bind the gas within them and prevent it from escaping, an immense gravitational well is required. Modified Newtonian dynamics and its extensions cannot supply such a well without invoking additional matter. If new matter must be invoked to explain the cluster scale, then the foundational purpose of modifying gravity begins to erode. A theory meant to eliminate dark matter cannot survive if it must reintroduce unseen mass to explain the largest structures in the universe. The cosmic microwave background stands as a further barrier. The temperature fluctuations imprinted on that ancient radiation are sensitive to the density of different matter components. They reveal how sound waves traveled through the early universe, influenced by the competition between gravity and radiation pressure. Dark matter is essential to this process. It provides gravitational wells that deepen the peaks and valleys of the temperature pattern. Without dark matter, the relative heights of these peaks cannot be reproduced. Modified gravity cannot substitute this effect without altering the early universe in ways that contradict observations. The microwave background is like a fossilized report card from the universe's infancy, and it grades modified gravity theories with unforgiving precision. Gravitational lensing adds yet another layer of difficulty. Because it measures mass directly through its effect on light, lensing provides a probe of the total gravitational field, independent of assumptions about luminous matter. Modified gravity theories can attempt to alter the relationship between mass and curvature, but they cannot easily reproduce cases where the gravitational field is offset from the luminous matter, as in the bullet cluster and other merging systems. In these collisions, the dark mass moves ahead of the slowed gas, creating a separation that modified gravity cannot explain. The gravitational map created through lensing shows mass concentrations where no light exists, matching exactly what would be expected if dark matter were real and interacting only through gravity. NASA's observations amplify this point by providing high-resolution images of colliding clusters. These images show that the hot gas, which contains most of the luminous mass in a cluster, experiences friction and slows down. The galaxies, acting like collisionless particles, pass through more easily. The gravitational mass, traced through lensing, follows the galaxies rather than the gas. This alignment would not occur if gravity alone were responsible for the discrepancy. It demands mass that behaves like the galaxies do, not like the gas. Dark matter possesses precisely that behavior. It interacts weakly, allowing it to pass through collisions unhindered, while luminous matter is slowed by pressure and shock. Even systems that are not colliding challenge modified gravity. Observations of large-scale structure show that galaxies cluster in patterns consistent with cold, dark matter. These patterns include correlations between galaxy positions, void sizes, and filament lengths. Modified gravity theories do not naturally produce the same coherence. The growth of structure over time depends on the balance between gravity and cosmic expansion. Dark matter accelerates this growth in ways that align with observations. Without it, structures would evolve too slowly, or their arrangement would fail to match what surveys reveal. The more data astronomers gather, the stronger the case becomes that dark matter is a genuine component of the universe. Gravity performs consistently, and whenever it appears to fail, it does so only if the mass content is assumed to be incomplete. Once dark matter is added back into the equations, every gravitational phenomenon aligns. General relativity remains intact. The cosmic tapestry begins to match reality. Through this long and careful process, the scientific community reached a consensus. Modified gravity theories offer insights, and some may one day contribute to a deeper understanding of space-time. But they cannot replace dark matter. They cannot describe the universe fully without reintroducing mass that behaves like the very substance they were meant to avoid. The simplest explanation remains the most compelling one. The universe contains an invisible form of matter. It does not interact with light. It does not heat or cool. It does not radiate or scatter. But it is there in vast quantities, carving the structure of the cosmos. With gravity tested and confirmed across cosmic scales, the next step is to explore how this invisible matter shapes the largest patterns in the universe. The cosmic web, with its sweeping filaments and immense voids, is one of dark matter's greatest achievements. Understanding how it forms and evolves provides essential insight into the nature of the unseen. The universe grows not from light first, but from gravity. Long before the earliest stars ignited, long before galaxies shimmered into form, dark matter began to gather in the silence of expanding space. It was cold, slow-moving, and able to accumulate into clumps, while ordinary matter remained too hot and energetic to settle. This early clustering created the gravitational seeds from which all future structure would emerge. Even when no light existed, gravity was already sculpting the cosmic landscape. The elegance of this process would later become clear as astronomers mapped the large-scale structure of the universe and compared it with theoretical predictions. The match revealed a profound truth. Dark matter is not merely an explanation for rotation curves or galaxy clusters. It is the foundation upon which the cosmic web is built. In the earliest stages of cosmic evolution, the universe was filled with a nearly uniform mixture of matter and radiation. Tiny irregularities, imprinted as fluctuations in density, set the stage for all that would follow. Ordinary matter was tightly coupled to radiation through interactions with charged particles, preventing it from clumping under gravity. But dark matter felt no such restraint. It moved freely, responding only to gravitational attraction. While ordinary matter was pushed and pulled by radiation pressure, dark matter began forming shallow wells of gravitational potential. These wells would grow slowly, drawing in more dark matter as the universe expanded. When the cosmic microwave background formed, releasing the last scattered light of the early universe, these gravitational wells had already begun shaping the distribution of matter. Soon after, ordinary matter cooled enough to fall into the wells carved by dark matter. This interplay between the visible and the invisible created the blueprint for galaxy formation. Without dark matter's early influence, ordinary matter would not have begun clumping so soon. Galaxies would have taken far longer to form, and the universe today would be far smoother, lacking the intricate filaments and voids we observe. As the universe continued to evolve, dark matter halos grew through a process known as hierarchical merging. Small structures formed first, merging over time into larger ones. This pattern is one of the hallmarks of cold dark matter. Because the particles move slowly, they collapse efficiently into localized regions. These small halos attract one another, merging into ever larger structures. The cosmic web emerges naturally from this sequence. Long filaments of dark matter connect massive nodes where galaxy clusters form. Between these filaments lie vast voids, regions nearly empty of matter. The visible universe traces this network with galaxies like droplets of dew on a spider's thread, following the gravitational blueprint laid down by the unseen. Simulations conducted on some of the world's most powerful supercomputers, including those operated by NASA, reproduce this process in exquisite detail. When researchers input the known laws of physics along with the presence of dark matter, the simulated universe evolves into a structure nearly identical to the one mapped by galaxy surveys. The filaments have the same thickness, the clusters the same density, the voids the same radius. Without dark matter, the simulations fail. They produce a universe that is too smooth and lacks the complexity seen through telescopes. The cosmic web is more than a visual marvel. It is a record of how gravity shapes matter across billions of years. It shows where galaxies will form, how they cluster, and how they merge. It reveals that galaxies are not scattered randomly, but gather along invisible pathways sculpted by dark matter. Observations from NASA's instruments, combined with ground-based surveys, have traced these structures across billions of light years. The agreement between observation and simulation forms one of the strongest pieces of evidence that dark matter exists. Within these dark matter halos, galaxies act like luminous seeds at the centers of vast spheres of invisible mass. They orbit within these halos, affected by gravitational forces far stronger than those supplied by their stars alone. Satellite galaxies cluster around giants like the Milky Way, their motions revealing the depth and size of the halo surrounding them. The halo extends far beyond the region of bright starlight, a silent guardian stabilizing the galaxy's rotation and anchoring its spiral arms. Even the merging of galaxy clusters reflects the shape of the cosmic web. Clusters gather along filaments, where gravity funnels matter into dense nodes. Their collisions occur along predictable paths, carved by the dark matter skeleton of the universe. These events, observed across billions of light years, reveal how dark matter behaves during extreme interactions. It passes through collisions largely unaffected, confirming that it interacts weakly with ordinary matter and with itself. Through every stage of evolution, gravity keeps serving as the universe's most faithful historian. It records where mass gathers, how it moves, and how it shapes everything from the structure of galaxies to the arrangement of clusters across cosmic distances. Dark matter is written into this history, not as a minor correction, but as a dominant presence. It determines the spacing of galaxies, the depth of clusters, and the size of cosmic voids. It shapes the universe on scales far larger than any star or galaxy. By the end of this long journey through gravity's revelations, one truth stands firm. The universe behaves precisely as though it contains a vast amount of invisible matter. Every map, every motion, every simulation supports this idea. Modified gravity cannot replicate these features without reintroducing something that behaves exactly like dark matter, and so the evidence leads inexorably back to the same conclusion. The unseen mass is real. It is physical. It is present everywhere, silently sculpting the cosmos. Now that the gravitational story is complete, the next question becomes how this invisible scaffolding grows into the immense cosmic web. Understanding the structure of the universe on its grandest scales leads directly to the next arena of exploration. The universe did not begin with galaxies or clusters or spiraling arms of stars. It began with a whisper, a nearly uniform sea of matter and radiation punctuated only by the faintest irregularities. These tiny fluctuations, so delicate that they could have passed unnoticed in a less patient cosmos, became the first clues to the vast and unseen architecture that would one day dominate the shape of everything. In those early moments, ordinary matter was restless, pushed and pulled by radiation pressure that kept it from collapsing. But dark matter moved quietly, listening only to gravity. It drifted toward the smallest fluctuations in density, gathering in pools that deepened as the universe expanded. These first wells of invisible mass formed the hidden blueprint of the cosmic web. Slowly, they stretched into filaments that reached across space like threads of tension, woven through an enormous and growing tapestry. Ordinary matter eventually cooled enough to fall into these filaments, settling into the gravitational channels created long before the first stars burned. As galaxies formed, they arranged themselves along the paths that dark matter had carved, clustering at the intersections where halos grew heavy and complex. The largest clusters emerged at the nodes of this web, fed steadily by streams of matter flowing along invisible rivers of gravity. Even the vast voids between these structures bear the signature of dark matter, for they are the regions where its density fell below the threshold needed to hold galaxies. These empty expanses expand as matter flows outward toward brighter filaments. Through simulations crafted on powerful NASA supercomputers, the entire life of the cosmic web emerges like a living atlas. The filaments extend and twist in patterns that match the maps created from deep sky surveys. The universe resembles a frozen storm of invisible currents, each branch shaped by dark matter long before ordinary matter evolved into luminous form. Galaxies move along these structures like leaves carried by a tide. Their rotations, mergers, and growth all follow the quiet choreography set in motion when the universe was young. Dark matter does not simply influence structure, it is structure. Without it, the universe would have remained smooth and dim, lacking the intricate patterns that now stretch across time. Everything we see is draped across an invisible framework, and the cosmic web stands as the greatest testament to that unseen foundation. To uncover this hidden architecture, NASA turned the darkness of the universe into a source of information. Light bends when it passes through gravity, and this bending becomes a map of whatever lies between the observer and the distant source. Through the Hubble Space Telescope, astronomers learn to measure the faint distortions in galaxy shapes that reveal the weight of the invisible. Each stretched arc and each tiny shift in orientation becomes a mark left by dark matter's sculpting hand. By collecting thousands of such distortions, Hubble produced detailed portraits of mass where no light exists. These portraits show halos surrounding galaxies, clustering around filaments, and drifting through space like shadows of the unseen. Chandra, observing in X-rays, uncovered another dimension of the invisible. Galaxy clusters glow with gas heated to millions of degrees, yet this gas requires enormous gravitational force to remain confined. Chandra's measurements revealed the depth of these gravitational wells, which far exceed what luminous matter could supply. When clusters collide, Chandra shows the gas slowing and heating while mass traced through gravitational lensing continues forward, proving that the unseen behaves differently from everything familiar. XMM Newton expands this view across the sky, searching for faint spectral fingerprints that might arise from particle decay. Though no signal has passed the tests required for confirmation, each observation sharpens the constraints that guide theory. Meanwhile, the Fermi Gamma Ray Space Telescope listens to the universe at its highest energies, searching for the quiet glow of dark matter annihilation. Faint excesses in the galactic center, subtle emissions from dwarf galaxies, and the general hum of gamma rays become pieces of a larger puzzle. None reveal a final answer, yet each narrows the path toward discovery. NASA's instruments work together like senses in a single mind. Hubble sees the distortions, Chandra sees the heat shaped by gravity, Fermi hears the universe whisper through high-energy photons, and the Roman Space Telescope will soon extend these searches across enormous swaths of sky, mapping dark matter on scales never before reachable. Through these tools, the invisible becomes charted not by its light, but by the consequences of its weight. With maps of the invisible in hand, the next ambition is to catch dark matter revealing itself through direct or indirect signals. This search unfolds at the edge of what instruments can detect, where statistics tremble and background noise becomes a labyrinth. The universe is filled with competing phenomena capable of mimicking the faint signatures that dark matter might produce. XMM Newton and Chandra revealed a mysterious 3.5 kilo electron-volt line, a narrow spike in certain galaxy clusters that stirred speculation about sterile neutrino decay. But the line appears in some environments and not in others, and its origin remains contested. It could be a door to new physics, or it could be a mirage formed by complex atomic processes within hot gas. Gamma rays offer similarly fragile clues. The Fermi telescope uncovered an excess at the center of the Milky Way that resembles the predicted shape of annihilating dark matter. Yet the region is dense with pulsars and turbulent processes that produce nearly identical signatures. Dwarf galaxies, ideal laboratories due to their low astrophysical activity, show no such excess, imposing firm limits on many annihilation models. Cosmic rays reveal an unexpected rise in positrons that once hinted at dark matter, but pulsars and supernova remnants can explain the same trend. Even radio halos in clusters, once suspected of carrying annihilation signatures, dissolve under scrutiny into more familiar cosmic activity. Through each investigation, the same discipline holds firm. A signal must appear where dark matter is abundant, scale with its density, remain absent in low-density regions, and survive every observational challenge across multiple instruments. No candidate has achieved this standard. The universe remains quiet on the particle identity of its unseen majority, offering hints but no declarations. Yet each unconfirmed signal narrows the space where dark matter can hide. Every false lead becomes a stepping stone. Every debate strengthens the rigor that protects the field from premature discovery. The search continues, sharpened by patience and illuminated by the faintest possibilities. The future of dark matter research is a horizon filled with clarity and uncertainty in equal measure. NASA's Roman Space Telescope will map the universe with a depth and breadth that transforms how we see the invisible. Its weak lensing surveys will reveal the growth of dark matter structures across cosmic time, exposing subtle interactions or confirming the perfect collisionless nature of the unseen. Cosmic microwave background missions will refine our understanding of the earliest moments, tightening the constraints on how dark matter seeded structure. Chandra and future X-ray observatories will test whether disputed spectral lines arise from new physics or from known atomic behavior. Gamma-ray missions will continue their watch over dwarf galaxies and the galactic center, pushing annihilation limits toward the faintest theoretically allowed rates. Meanwhile, laboratory experiments such as LUX-Zeppelin, ADMX, and IceCube will probe the particle side of the mystery, guided by the astronomical constraints NASA provides. Together, these approaches form a unified exploration of the unknown. The next decade may bring the first direct detection of a dark matter particle, a moment that would bridge the cosmic scale of astronomy with the quantum scale of particle physics. Such a discovery would reshape the foundations of science, opening new avenues into forces, symmetries, and particles that lie beyond the standard model. But if no detection comes, the implications are equally profound. It would suggest that dark matter interacts even more faintly than imagined, or that its nature resides outside our current theoretical landscape. Either outcome carries the promise of discovery. For now, the invisible remains a silent architect, shaping galaxies and carving the cosmic web without revealing itself. Yet, every lensing map, every X-ray spectrum, every gamma-ray observation, and every underground detector brings us closer to hearing its voice. The universe has left a trail of gravitational footprints across billions of years. Following them is the greatest scientific journey of our time, and somewhere along that path, the unseen will eventually step into the light.